Lesson 6.3, Perform Function Operations and Composition. In this lesson, we'll take a look at multiple functions, add, subtract, multiply, and divide them. We're also going to revisit domain of functions, as some domains will be unique depending on the type of function you're looking at. Lastly, we'll take a look at composition. We'll start by just looking at evaluating functions. Hopefully this looks like review. It says let f of x equal 2x plus 4 and h of x equal 3x to the negative 1 minus 2. To evaluate a function, it asks you to plug in something for the input and determine the output. We've done this before. F of 2 means when x is 2, what is the value of our function? So we plug it in on the left side and the right side. Hopefully this looks completely familiar to you. Where you see x, plug in 2 and then simplify. 2 times 2 is 4. 4 plus 4 is 8. What that means is f of 2 equals 8. When you have a different kind of function though, like the next one, h of x, you're asked to evaluate h of 6. So when we plug in h of 6, we would get 3 times 6 to the negative 1 minus 2. Now we have to think about order of operations. The 6 is the only thing that has that negative exponent. What that means is we need to take the reciprocal of the base. The 3 is going to stay on top and the 6 actually moves down to the bottom. Minus 2. 3 over 6 reduces to 1/2. Minus 2, you'd want to get a common denominator, so I'll put that 2 over 1. A common denominator of 1 and 2 is 2. I can just change my second fraction by multiplying top and bottom by 2. This would give us 1/2 minus 4/2. And 1 minus 4 would become negative 3. And we end up with negative 3 over 2. Now when I ask to state the domain for each of the functions, we have to state it specifically for h of x, and I'll show you why. When asked to find the domain for f of x is a linear function, which means the graph would just be a straight line. When you have a linear function, the domain is easy. It's all real numbers. So we just write x equals all real numbers. You can plug in anything you want for x and get a value for y. But for h of x, the exponent is significant. We have x to that negative 1. By definition, for h of x, it's not linear. If you simplify that radical, you'd have 3 over x, or rational exponent, or just exponent, I should say. It actually becomes 3 divided by x minus 2. And what makes this unique for the domain is x is in the denominator. And in a fraction, denominators can't equal 0, which means for this case, x can't equal 0 would be the domain. Luckily, we only plugged in 6, so we were able to get an output value. But if we tried plugging in 0, we'd end up with 3 divided by 0, and that's not defined. When working with multiple functions, we can add, subtract, multiply, and divide them. We have f of x equals 5 times x, and g of x equals x plus 2. The operation for addition, subtraction, multiplication, and division are as such. Addition simply means you add the two functions together. That's pretty straightforward stuff. If f of x is 5x, and g of x is x plus 2, and we add them together, technically we wouldn't really need that parenthesis for that second function. We would just get 5x plus 2, and that would equal 6x plus 2 when you simplify. Subtraction, well, subtraction's always particular for us. When you subtract, it's going to be significant to have the parenthesis in that second function. If we take f of x minus g of x, it's important to note that you have to distribute the negative into both parts. You're subtracting the x and the 2. That gives us 5x, that's an equal right there, minus x minus 2. And if we combine like terms now, we end up with 4x minus 2. That would be the subtraction problem f of x minus g of x. For multiplication, you'll either have the dot in between them or you may have nothing in between them. They're just written side by side. That will simply mean we multiply. It could be a distribute, it could be a FOIL, it just depends on the type of function you have. Since 5x is just one term, we can distribute it in to the x plus 2. Being careful to make sure we distribute both the 5 and the x to both parts on the inside. If we take 5x times plain x, that's 5 times x squared. Plus 5x times 2, 5 times 2 is 10, we'd have 10x. Hopefully the first three functions seem fairly straightforward. When we have division, division is kind of particular like subtraction. The key thing to note for division is, we'll just set it up first, sorry. We'll set up the fraction and then I'll tell you why it's significant. If we do f of x divided by g of x, we would have 5x in the numerator divided by x plus 2 in the denominator. I'm going to put that x plus 2 in parentheses because we can only simplify the fraction if we have parts that match exactly on the top and the bottom. So even though we have an x in the numerator and an x in the denominator, the x in the denominator is in a parenthesis being added to 2. We can't cross them off unless there was a separate x on the outside. And the other thing to note is now you have an x in the denominator. So we have to be careful here and recognize that g of x, whatever's on the bottom, can't have an output of 0. So that's something that's going to be particular for division. When you write out your quotient, if you have a variable in the denominator, we need to figure out, well, how will this affect our domain value? All of our values up above, the domain was all real numbers for each solution. But for this one, with that x in the denominator, what we want to say is for our domain, g of x can't equal 0. We're going to follow this definition. If g of x is x plus 2, we have to start off by saying x plus 2 can't have an output of 0. That would make the denominator undefined. From here, we need to get x by itself, which isn't too difficult. If we subtract 2 to the other side, the domain would then become x can't equal negative 2. That must be included if you ever have a restriction. Things to look for are that variable in the denominator, or like before, if you have a rational exponent or a negative exponent. I should have had that typed in there. So let's add that in, please. If you have a rational exponent, we have to be careful on that, or a negative exponent. Otherwise, the rest of them should be all real numbers. It says, let f of x equal 4x to the 1/2 and g of x equal negative 9x to the 1/2. Find the following. We start off with addition, f of x plus g of x. If we take 4x to the 1/2 plus negative 9x to the 1/2, we first have to decide, do we have like terms? And we in fact do. The x's have the same exponent. That means we can simply combine the coefficients out in front. 4x to the 1/2 plus negative 9x to the 1/2 would result in negative 5 as your coefficient, x to the 1/2. Notice we're adding the coefficients. We're not changing the value of the exponents. For b, we're subtracting f of x minus g of x. If we take 4x to the 1/2 minus negative 9x to the 1/2, we recognize that that double negative in between the terms would actually change them to plus. And if we have 4x to the 1/2 plus 9x, we'd get 13. X to the 1/2 power. So adding and subtracting, not too bad, but then it asks us to find the domain. What will make the domain for each of these functions unique is the fact that the variable has a rational exponent. So for both f of x and g of x, since the variable is the same, they're going to have the same domain, which is kind of nice. If you have x to the 1/2, thinking about what that technically means, that's the same as the square root of x to the first power. So think to yourself, what kind of numbers can we plug in for x that would be valid? We could plug in perfect squares. Those are easy, like 4 and 9 and 16 and so on. You could plug in other numbers that would give you decimal answers. We could even plug in 0. We had that on one of our slides in 6.1. The square root of 0 is 0. The only numbers we can't have are negative numbers, because the square root of a negative number is not a real solution. If you recognize that x can't be negative, think about writing our domain in a way that represents all the possible values it can equal. It can equal 0 and anything bigger than 0. If you state the domain as x is greater than or equal to 0, that would be true for both f of x and g of x, whether it's in radical form or rational exponent form. All right, let's try the 2 on the bottom. M of x equals 6x and n of x equals 2x minus 4. As we look at this set, we have c and d. C is multiply. There's a little star in between them. That's the same as a dot, so we'll multiply. And then d is going to be our division. If we multiply 6x and 2x minus 4, kind of like the example on the last page, we'll distribute the 6x into both terms. 6x times 2x would be 12x squared, minus 6x times 4 would be 24x. There's your product. For d, m of x divided by n of x, this one gets a little tricky, so make sure to follow along. If m of x is 6x and n of x is 2x minus 4, there's your quotient as is. But here's something that we can do on this problem that we couldn't do last time. We can factor out the 2, and then that becomes, I'm just going to equals there and it equals here, 6x, and then on the bottom, if we have factor out that 2, we have x minus 2 left over. Now, what makes this so much fun for us is the 6 in the denominator, or excuse me, in the numerator, and the 2 in the denominator. Since they're not part of addition or subtraction, we can reduce them. The 6 times x, we can break apart the 6 and the x without addition or subtraction. What this means is the 2 goes into 6 3 times. And that would give us 3x over x minus 2. That would be the simplified product, or excuse me, quotient for m of x divided by n of x. So let's think about our domain for c and d. C and d are actually going to have different domains. For c, that would be the product. The domain is all real solutions or all real numbers. If you're just multiplying something by itself or by something else, I'm trying to think and write at the same time. I need to not do that. If you're trying to multiply two functions together, that's ultimately what I meant. You can square anything and you can multiply anything by 24. Therefore, the product would be whatever you need it to be when you plug in a value for x. For d, however, if you make it a quotient, now we have to think about that rule with 0 in the denominator. Since we have x minus 2 in the denominator, we know that whatever that solution is, we can't have a value of 0 when we're done. So we write x minus 2 can't equal 0. To get x by itself, in this case, we'll add 2. The domain for that product then is x can't equal 2. So what that means then is it can be anything else except for positive 2. The last thing we have for lesson 6.3 is composition. It says the composition of f of x and g of x is f parenthesis g parenthesis x. This would be the composition. And that's read f of g of x. We always read it from left to right. So whatever the letters on the outside, that's where you start. But we actually calculate our solution inside out. Composition is where the output of a function becomes the input of another function. So that h of x equals, we're actually not going to even write that in our work. So I wouldn't worry too much about that part of the definition, but the f parenthesis g parenthesis x is going to be our focus. The examples down below. Let f of x equal 3x minus 8 and g of x is equal to 2x squared. Find the following. It says g parenthesis f parenthesis 5. That means g of f of 5. We want to evaluate inside out, which means we're going to actually find the output for f of 5 first. So there are only going to be two steps. The first step is to evaluate that inside function, f of 5. So wherever we see x in the f of x function, we plug in 5 in its place. 3 times 5 minus 8. 3 times 5 is 15, and 15 minus 8 is 7. There's step 1. That's the output for f of 5. The definition for composition is the output for one becomes the input for the other one. So if we substitute 7 where we saw f of 5, we're going to plug in 7 in the g of x function, since g of x is on the outside. If x is 7 and g of x is 2 times x squared, we'll take 2 times 7 squared. 7 squared is 49, and 2 times 49 is a total of 98. The last number that you get is the value of the composition. Watch what happens when we flip the order around. If I take f of g of x, we might not get the same answer. What this means we're going to do is we're actually going to evaluate g, hang on, we'll get back there. We're going to evaluate g of 5 first. So we're going to work inside out. G of 5 means we'd have 2 times 5 squared. 5 squared is 25. 2 times 25 is 50. That's our output. By definition, the output for one becomes the input for the other one. So on the outside, we had f of x. We're going to evaluate f of 50. In the f of x function, it's 3x minus 8. That means we're going to do 3 times 50 minus 8. 3 times 50 is 150. And when we subtract 8, we get 142. That would be the final answer for the composition. Notice in example C, we have f of negative 2. What that means is going to happen is we're going to plug the value for our answer back into itself. How strange is that? Well, let's see what we get. We're going to evaluate f of negative 2. That's step 1. If x is negative 2, and we take 3 times negative 2 minus 8, 3 times negative 2 is negative 6, and if we subtract 8, we get negative 14. So that output is the new input, but notice we're going to plug it back into the f of x function since f is on the outside and the inside. We're just going to plug it back into f of x again, but now we're going to substitute in negative 14. 3 times negative 14 minus 8. 3 times negative 14 is negative 42. If you subtract 8 from negative 42, we get negative 50. All right, you guys try the last one, g of negative 2. Once you get your answer, press play and we'll see how you did. All right, did you get 128? Be careful when you plug in negative 2 in the very first round. Remember, negative 2 squared gives you 4, and 2 times 4 would give you 8. That output then gets plugged right back into the same function. 2 times 8 squared, 8 would be positive 64, times 2 is 128. We will complete the rest of these problems in class tomorrow. So this is lesson 6.3.